Hello everyone, I'm Zaiwei Zhang from UTLST. Today I will talk about our project H3DNet, which is 3D object detection using hybrid geometric primitives. The task is that given a 3D point cloud of a scene, our goal is to detect oriented object bounding boxes from objects in the scene. Object detection is one of the most important visual recognition problems, and there are many approaches. Our approach is motivated by a recent line of works that formulate object detection as a regression problem, including both the works in the 2D domain and the works in the 3D domain. These regression techniques depend on how to encode the bounding boxes. One previous approach, WONet, is to describe an object as object center plus object sizes. However, this approach may be limited in the sense that if center prediction is wrong, then there is no way to recover from that. Here are two common failure cases for WONet. For irregular shaped objects such as window and door, it's hard to detect the center location. Additionally, with just object center prediction, it's also hard to predict the bounding box boundaries, which will cause the size prediction wrong. In contrast, we consider multiple encodings that include the box center, 6 face center, and 12 edge centers, in total 19 geometric primitives. They provide an overcomplete set of constraints, and one can tolerate wrong predictions in these geometric primitives. Intuitively, they are suitable for different categories of models. For example, box centers are suitable for solid objects, while face and edge centers are suitable for objects where face and edge features are prominent. The overall network architecture consists of 3 modules. The first module is for predicting geometric primitives and their associated features. We use a tower of PointNet backbone to extract features. The second module is for generating initial object proposals by regressing them to the initial primitives. And the last refinement module aggregates the predicted geometric primitives and their features to refine the predicted bounding boxes. Let's first look at the geometric primitive prediction module. We use PointNet backbones to extract a proponent feature and also predict related object masks, object face and object edge masks. We then apply a multi-layer perceptron to predict the corresponding geometric primitives, which are object centers, object face, and edge centers. For the proposal generation module, we first use the object centers to predict an initial set of object proposals, and then we connect the initial proposals and the geometric primitives with a distance function. The distance function uses robust norm, and the initial proposal module uses the distance function to fit box parameters to the predicted geometric primitives. Backpropagation can be done via the implicit function theorem. Let's take a closer look at the proposal generation part. For beta visualization, let's look at the highlighted crop of the original scan. We can see the detected face and edge centers on the object. For initial bounding box proposals, we can project its predicted center to each face and edge. Within a range, we can find its matching geometric primitives and connect them with the distance function. We then apply the refinement modules. It aggregates features associated with these geometric primitives, which contain contextual information to refine the box parameters. Results on benchmark datasets are quite encouraging. We improve from the state-of-the-art by 8.5% in MAP at 0.25 threshold, and more than 14.6% in MAP at 0.5 threshold on ScanNet v2. In addition, if we remove the object proposal refinement just using hybrid features learned with different geometric primitive prediction tasks, we can see that the performance gains are much smaller, which shows the importance of our proposal refinement module. We also have noticeable improvement on SUN RGB-D v1. The improvements are also consistent across all the categories, particularly for some objects such as window, door, shower curtain, our gain is significantly higher. Those objects are irregularly shaped, which is hard to detect just using object center, but easier to detect with face or edge centers. We show some qualitative examples of the predicted face and edge points here. As shown in the figure, the face and edge labels are dense and contain sharp geometric shape feature. Our prediction results are also dense and accurate. Here we show qualitative examples of object detection results with VONet, our approach, and ground truth. We can see that our approach overall is better, and for detecting thin object or object with strong face or edge features, such as windows or doors, our results are significantly better. Next, we look at the ablation study. As we remove the refinement module for center, size, semantic, object existence, and object angle individually, we observe that size and object existence are affected the most. With edge and face center prediction, the boundary features are extracted more, and it leads to better size prediction. Also, more object geometric features increase the confidence for object existence prediction. We also show some qualitative examples in here. Now we evaluate the importance of using different geometric primitives. Here we show the covariance matrices of ScanNet and SUN RGB-D of the primitive prediction result. We can see that both covariance matrices are well approximated by diagonal matrices, which shows no strong correlation between different geometric primitives. Also, as we use only edge or only face centers, there are different performance drops across multiple categories. As shown in the figure, only by applying both geometric primitives, we are able to achieve the best result. Finally, we study the performance changes with different number of computation units, which are pointed backbones. As shown in the table, with the increasing number of computation units, our performance gains are continuously increasing without overfitting issues. With only one pointnet backbone, our model size is similar to VONet, and our results are significantly better. However, for VONet with 4 pointnet backbones, they only achieve marginal performance gain on ScanNet and no performance gain on SUN RGB-D. In conclusion, we formulated object detection as regressing and also aggregating an overcomplete set of geometric primitives. We proposed multiple types of geometric primitives that are suitable for different object types and things. And we achieved state-of-the-art 3D object detection results on SUN RGB-D and ScanNet with only point cloud. This is the end of our presentation. Thank you.